Gather round the campfire, everyone. We're going to do some maths with Nick. In fact, we're going to do some set theory today for those of you interested in such things. Before we do, don't forget to check the link down in the description for the My Headspace cram courses that we're running before each exam. Get yourself fighting fit and ready for the next day. All the information is in the link below. Group theory, what do we got? Group S is formed of the set of permutations of 1, 2, 3, 4 under the operation of composition. Now, before we get going, let's just understand what that means. It means, for example, we're going to write them all like this, based on how the question's formulated, and we could have element 1 being mapped to element 2, element 2 being mapped to element 4, element 3 being mapped to element 1, and element 4 going to element 3 at that point. All right, and that's what we mean, is how we're going to shuffle these numbers around. Okay, so the first element becomes the second one fourth, third one first, fourth one third, obviously. Okay, so this is how we're going to write down the elements of these things. Now, composition would mean if I did 2 of them, so 1, 2, 3, 4, and this one goes, I don't know, 1 to 3, 2 to 4, 3 to 1, 4 to 2. The composition of these two, we're going to use the little bubble, would be 1, 2, 3, 4. We're always going to start 1, 2, 3, 4. So element 1 goes to element 2, element 2 goes to element 4. So overall 1 has gone to 4. 2 goes to 4, 4 goes to 2, goes to 2. 3 goes to 1, 1 goes to 3. 4 goes to 3, 3 goes to 1. All right, that's what we're talking about here. Okay, so sometimes with these pure maths questions, it's important to get your head around what on earth we are actually talking about. And some examples can help that. What's the identity? Well, I hear you say. The identity is just the element that maps something to itself. Write down, which means it's obvious. Well, 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. What is the opposite? What is the inverse of element A here? Well, the inverse has to get us back to where we started. So if 1 goes to 3, 3 has to go back to 1. If 2 goes to 4, 4 has to go back to 2. If 3 goes to 2, 2 has to go back to 3. And if 4 goes to 1, 1 has to go back to 4. Swippy swappy. Paying attention? Good. Right, now, associativity. Oof. You're going to have, yeah, we'll have space for this. So really what we need to show is that if I do the composition of B and C, and then I do the composition of A, that is exactly the same as doing A on B on C. All right, so let's B on C. We're going to need B, 3, 4. We're going to need A on B, 1, 2, 3, 4. And we're going to need A on B on C for 1, 2, 3, 4. Right, we are going to go, like the notation I'm going with here is we do the one on the right first and then the one on the left. We could define all of this going the other way around, it makes no difference. This is how we're defining it, okay? Basically, I'm following the same thing as composition of functions, right? So if you go f of g, you do g first and then f. So I'm following that idea. So C followed by B. So what does C tell me? 1 goes to 4, and then B tells me 4 goes to 1. What about 2? 2 goes to 1, 1 goes to 2. 3 goes to 2, 2 goes to 4. 4 goes to 1, 1 goes to 4. Remember that? I must have got 3 wrong. 3 goes to... Ah! What am I doing? That's wrong. Right, let's do that again. Where does C go? All right, we're doing C first, right? 1 goes to 4, 4 goes to 1. 2 goes to 1, 1 goes to 2. 3 goes to 2, 2 goes to 4. 4 goes to 3, 3 goes to 3. Right. Mild issue there. We got there in the end. So now we're going to do this one followed by A. So where does 1 go? 1 goes to 1, 1 goes to 3. 2 goes to 2, 2 goes to 4. 3 goes to 4, 4 goes to 1. 4 goes to 3, 3 goes to 2. Oh, did I get that right? We'll find out. A on B. So 1 goes to 2, 2 goes to 4. 2 goes to 4, 4 goes to 1. 3 goes to 3, 3 goes to 2. 4 goes to 1, 1 goes to 3. I know I get it right. Well, I hope I get it right if these numbers are no repeats. That's how I knew I was mucking up earlier. All right, so we're going to do C followed by this one. So C takes 1 to 4, 4 goes to 3. 2 goes to 1, 1 goes to 4. 3 goes to 2, 2 goes to 1. 4 goes to 3, 3 goes to 2. And the important thing is, this is associative because these two permutations are the same. Now obviously this is not sufficient to show it is true for all of it, but it's a nice little snapshot. You'll find mostly in group theories that associativity is inherited from the operation. And we tend not to prove it, because to prove associativity on a bunch of general ones of these would be annoying. Okay, is it possible to have a subgroup of order 4? Now, we're not saying there is one, but is it at least possible? Is it something that I can rule out, yes or no? Well, the real question is what is the order of the group, right? What is the order of S? i.e., how many elements does it have? Well, we want to look at how many permutations of the numbers 1, 2, 3, 4. Well, we know this. How many ways can you order 4 elements? It is 4 factorial, which is 24. And one of the main rules for subgroups is the order of the subgroup has to divide the order of the parent group. Now, so is it possible to have a subgroup of order 4? The answer is, my young friends, yes, as 4 divides 24. The real one is, could we make one? Right. This is not in the question, but do you know what? We're here, let's do it. We're hanging out, we're having a good time doing some group theory. So, can we make one? One of the easiest ways to make a group of a certain order is to make it cyclical. Now, you can get cyclical groups with prime orders, but order 4 is going to work for us because we've got this pattern. And really, what I just want is a generator. Okay, so 1, 2, 3, 4. And the obvious small group of order 4 that will be self-contained, will be closed, etc., is this nice cyclic one where 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. Then if I do that again, 1 goes to 3, 2 goes to 4, 3 goes to 1, 4 goes to 2. If I do it again, 1 goes to 4, 2 goes to 1, 3 goes to 2, 4 goes to 3. We're just shifting them along. And then e to the 4 should be my identity at that point, which is 1, 1, 2, 2, 3, 3, 4, 4. So there we go. It's possible, certainly, and in fact, I've created one. It has an identity. Does it have inverses? I think e and e cubed are inverses of each other. 1 goes to 2, 2 goes to 1, 2 to 3, 3 to 2, 3 to 4, 4 to 3, 4 to 1, 1 to 4. And I would assume e squared is self-inverse. And it is. Bosh. Easy peasy, squeeze the lemon. I'm Nick. This was Group Theory. If you enjoy this, don't forget to like, subscribe, hit the bell so you get all those sweet, sweet notifications. Bing! Every time we drop one of these. And hopefully, I will see you next time.